Hello, welcome to Chapter 11 lecture. This chapter, we're gonna talk about performance tuning in terms of, it's gonna touch upon the hardware, which you should have already gone through the infrastructure lecture video. So this is kind of now tying to that infrastructure component. We'll look at how, what we can do at the database layer that will sit on the hardware and how we can optimize and make sure the performance of the system in terms of all the inputs and output can be optimized. So let's go in and take a look. Objectives. All right, so start off with the database performance tuning concepts. So in a nutshell, at the end of the day, the user that's using an application, or it's called the end user client side, right? Whether or not the user is using a database, using an application that's installed on their computer, and or they're using the website, the application that where the user is interacting, they're the one that wants to experience the performance, or they get impacted by the performance or lack thereof. So the end user expects the system to respond when they interact with a computer or application. Every time they do that, the application then reach out to the database server or database layer and say, hey, here's what I need, and then here's the SQL, and so on and so forth. So performance tuning is literally at the database side. How can we allow the database to not hinder the response time? So as queries comes in, and then the database needs to handle all of that and sends it back out with whatever the result that was generated. That's kind of what performance tuning in terms of database is talking about. So obviously the goal is to execute query as efficient, as effective, as timely as possible. And again, keep in mind, a single database may not be just dealing with one particular application. A database is a centralized collection of all the assets and information. So when you centralize data into one source of truth for an enterprise, you will likely have multiple applications, websites, or other applications accessing the same database. So the database may not be just be supporting one application. Depending on how you design the database, it may end up supporting multiple applications that tailor to multiple business operations, multiple user groups, and the database is the central point or potentially the bottleneck for responding to those users' expectations or requests. So this chapter looks at certain component or concepts about how we fine tune to make sure that bottleneck is minimized, all right? So we talked about this. I'm not gonna spend too much time on it. Again, I did the whole lecture on infrastructure. So this is just kind of description of what they are. CPU, RAM, storage, and so on and so forth. So make sure if you haven't seen that lecture, just go back and see that one, because it really gives you a solid foundation that kind of, for the rest of this chapter, we'll relate to some of those things that I discussed in that infrastructure lecture. So make sure you go through that lecture as well. All right, so client server. So client-side SQL performance tuning and then server-side SQL. So remember, a SQL is nothing more than a series of statement, which we call the SQL query, that gets sent to the database. So when the SQL, that statement can be generated at two different places or any places outside of the database. For example, you can generate the SQL at the application layer or at the front end, the client side. So if I install an application on my computer and then I use it, but then the computer actually needs the network to talk to the database somewhere in the corporate headquarters. Even though the software is installed on my computer, the data is actually not here. So it relies on my software on my desktop or on my computer to compile and generate the query that's kind of built into the application. So as they develop this application, they develop what query need to be structured or put together and then sent over the internet to then access a centralized headquarter database for what I wanted to accomplish. So that's kind of known as the client side SQL. And then obviously server side, sometimes your application can trigger a predefined, pre-written SQL procedures that's actually housed and stored and compiled at the server side near the database. So again, it's all just where the SQL is actually originated, whether or not it's at the client side or the server side. But either way, the performance of that SQL can be tuned. So when you compile a lot of SQL at the client side, what you're actually doing is you're letting the computer power of the user, right? I have a laptop in front of me. So if the application has the duty of compiling the SQL statement and then send it over the internet to the database, I'm actually using the CPU and the RAM power of the user to do that work. That overhead is consumed by the user side computing power. Whereas if you are asking the server to compile and execute or send over to the database those SQL queries, you're actually using the server side RAM and CPU and memory power to help you accomplish that, which then you're transferring the overhead, right? The raw power and resources you're tapping into the server. So there's a trade-off here. One is, internet speed. If you compile a lot of stuff at the user side, client side, you benefit from, you don't need to consume too much resources on the server side because you offload that to the client. But then you're now hindered by how fast the internet speed can transfer all of that back to the database so database can do what you want it to do. Whereas if you want to bypass the internet, potential internet inefficiencies, then you have the server help you do that, but at a cost of then the server has to consume and expense the overhead to compile those. So those are the things that as part of performance, we can try, test, evaluate to see which route will work better based on the context of what you're building or what the applications are for. So database management system architecture, in terms of physically, what does the database actually look like inside a hard drive? Quite frankly, it doesn't look like Excel. So when we actually look at data, whether or not you're looking at Access database or the earlier lecture where I showed you online-based the MySQL database, you saw an interface where I can also type some SQL queries. And then the return result shows kind of an Excel looking like table that's kind of generated from my SQL statement. All of that are just presentation layer that structured what the database provide back to me. And then the application formatted to make it look familiar to me. So they put it into a table or Excel looking like interface. But that is not actually physically how it is stored. What's stored on the hard drive is nothing more than a series of zeros and ones that actually doesn't make a lot of sense for anyone looking at those sequences. In other words, the only component that can decipher the actual files, that makes up your whole relational database. And each one of those files are nothing more than a bunch of zeros and ones that if you open them up, it doesn't make any sense and you can't really decipher what actually is in that file. And the database actually maintains thousands and thousands of this type of file that actually makes up your database. So it requires the actual database management system, the software, to know how you actually decompose all your data into all these files, how to put them back together, where to find what data, what cell, what attribute, what table, what relationship. It's only understood by the database. So the database controls that placement of files that makes up your whole database. So as you retrieve them or you store them, that's what the database engine do. Their job is to manage and govern the zeros and ones all the way from the physical placement on the disk and where to locate them and group them all the way to pulling it back where then you can see it the way that we can understand what's actually inside the table or what are the attributes and so on and so forth. All right, so that is the architecture. Let's see. So cached, just like any type of memory in a computer system, a cache memory is allow you to store something in a temporary location. So when you run a SQL statement, the actual statement that was compiled and sent for the database to run are actually stored in a temporary memory or the cache memory. And then once it gets executed and certain time period have passed and the new ones comes in, the old ones that were executed actually gets purged out of the memory because, right, you don't have unlimited memory that's gonna house every single statement at a standby for the CPU to go grab and execute and then execute the instructions. So SQL cache is literally that. There's a memory space allocated for SQL statements at the ready. And then they're inside the memory, so they're fast, right? They're in the kind of a, instead of the hard drive, they're in the temporary memory like RAM or cache memory. So so to work with data, a database management system have to retrieve the data right from the permanent storage. So once your SQL is ran, it actually pulls the data that you asked for from the hard drive, which is known as the permanent storage, and place them into the RAM, which is, you know, temporary storage. So now that it's inside the RAM, it's housed there until your application goes in and retrieve them and then display it the way that we want to see it or the application want to present it to us. So database will do that. They retrieve data from permanent and then they place it into the RAM, and then your application go to the RAM and then pull that out and then to present what you're asking for. So that is kind of the, again, the use of hardware component of how database and application and the hardware and the memories work with each other. So referring back to the infrastructure, right, I talk about input and output and hard drive or your hard drive or permanent storage being your slowest, the longest pole in the tent that takes, you know, most of the resources or has the most inefficiencies when it comes to passing zeros and ones between all the CPUs, RAMs, cache, and hard drives. So this is what this particular slide is referring to. So this is a image of it. So if you kind of, you know, logically trace this through, you have database management servers. So you have one physical server, that's what it's representing. And then you have a hard drive, which has data such as your tables, your attributes, that's chopped up into files, zeros and ones that get stored on your hard drive, your database. And then you have a database management system process that runs to listen for incoming requests or incoming SQLs, right? So if any SQL is coming in to request the database or from the drive, the data, the SQL will cache that instructions. You'll cache the return data values. It has a job of scheduling when the cache gets, when the SQL gets run. It locks, right? It optimizes. So everything we talked about in chapter 10, it's all performed by the database. So this is kind of like a listener that just stands by and listens for instructions. And once it's triggered by an incoming SQL query, you know, listeners understood something just came in, and then he activates all this component. And once this component activated and executed, he then requests an IO for the actual zeros and ones to come back, and then sends the result back to the client. And the client again can be, you know, a web application and or your whatever you install on your computer that need to talk to a database remotely. So that's kind of, again, logical flow of how this whole thing works. Components that you've seen from chapter 10 is encapsulated in here as well. All right, so now in terms of optimization, what kind of modes or different, I guess, approaches you can think of that way. So database has a couple options to optimize itself. Obviously, you have fixed amount of resources, such as how many CPU cores, how fast the CPUs are, how much space in the RAM, how much space you have in the cache, and so on and so forth. So at the end of the day, those are not infinite. They're pretty defined resource that has certain capacity that the database can utilize. So you need to use algorithm to look at between the incoming queries and what you have available to you at your disposal, and then come up with the optimized way of getting the user what they want. So database query optimization modes kind of look at and relies on algorithms to do statistical analysis of how best to deal with all this stuff. And let's see. So evaluates based on timing. And we'll go into a little bit detail of some of the component that kind of defines a little bit more than just the word algorithm. Let me see here. I think checking my notes. All right, so next one. So what are the modes? Two specific modes, automated or manual. So it's pretty much what it says. If it's automated, you're actually telling the database, you know what, you go figure that out. You have a component, you're capable, do your thing, right? Use the stats, use the use the algorithm, and then draw your own conclusion, and we will trust you doing that. So then if you set it to that mode, then the database will always find, based on its capability, to find the most cost-effective way to run its SQL statements, to run its its tasks. Or you can do a manual optimization, which then requires the database administrator to select and schedule certain things based on how we know what we're asking the database to do. So we can set certain rules about how we want the database to address optimization based on the criteria that we set manually. So that's kind of just two ways of doing it. I think conceptually, why will you choose one versus the other? One example will be, you will probably go automatic if you're not really, your database is not really loaded with tons of concurrent, tons of user, massive amount of data. So if you're not dealing with that kind of environment, automated may be effective. So it all depends on the context of what your database is trying to satisfy, between the users, the expectations, the complexity, the concurrency, and then the business rules and logic that your SQL statement usually involves in. So you will take that into consideration to kind of decide, should I use automatic or should I use manual, one way or the other. So that's it. That's just kind of how you can leverage the database to help you optimize and the component of doing that. And then you have static query. This deals with kind of the timing. So you have static and you have dynamic. So in a static, in a nutshell, it's an optimization strategy selected when the query is compiled by the database. So in other words, you have predefined, pre-written SQL statement at the ready that doesn't really change. It just gets run at a fixed time. So a lot of, for example, a lot of maintenance, right? At the end of the day, we need to scan the database. We need to rebuild indexes. We need to check certain integrity. We need to run certain, generate certain temporary tables. Those are SQL statements that's already kind of defined, written, and they're static. So in that case, right, you have that option, and then the dynamic optimization access strategy dynamically determined by the database at runtime using most up-to-date information about the database. So they take into, at the moment in time, what does it have, right? At a given time, I may not have full resources allocated to the database because of people are using it, some other process is running. So I get to choose based on additional variables at the point in time when I need to execute certain things. I change the strategy. I change how I want to optimize, how I want to stack the instructions. So that's it. So one is at the time, or one is predefined regardless of at the time. So static versus dynamic. So in terms of static, the approach is common when your SQL queries or statements are kind of embedded into your programming code, because right, those codes gets run based on the application, and then based on the specific users of those applications. While the dynamic one, database access this strategy during the execution. When I have to run this query, I will take in other factors and considerations to determine at the time of running how I want to handle the strategy to make sure I'm still optimized. All right, let's see. So you can imagine for a database to calculate optimization based on certain constraint of resources availability, of all the hardware component, plus the complexity of what you're trying to run and what the database is expecting to generate, right? If you write a SQL statement that's very simple, you're asking for one single record, that's one request that has a statistic element to it. That it's a straightforward SQL, it's one single statement, it's not complex, and you're expecting to see 5 different data points coming back. Or is this SQL that I'm about to run is gonna generate 5 million rows of records coming back based on how the statement is, what the statement is asking for. So as you can imagine, right? So everything is statistically based for the database management system to compile the algorithm to determine, or utilize the algorithm to determine optimization. So for those of you that took stats class already, I believe you guys probably have to learn about constraints, right? You can use linear charting based on multiple constraints to find how the lines intersect. Each line represents a constraint, a variable of constraint. And there's a statistical concept where if you lay out in a linear format to represent all the different constraints I play, visually, mathematically, statistically, you can then pinpoint the maximum and minimum cross points based on multiple intersecting lines. So that's where all this comes in. We apply statistical concepts, or database world applies that into the database engine to use statistics to provide information about database characteristics. And for example, you had to evaluate size of the database, number of records in those tables or in the database as a whole. What's the average access time when you access this table based on all the historicals of this database handling people asking stuff from each of the tables or the queries they write. All of that stats and data are also kept and maintained by the database so that you can continue to learn the variables that speaks to the characteristics of how this particular database is performing. And then those historical data points are constantly compiled and factored into optimization strategy by the engine to determine how to execute best based on what's asked. So those are all important things. Statistics is a key component into optimization. Let's see. So other measurement that the database or consider in terms of characteristics in the statistics is right number of processors. Like in the infrastructure lecture I talked about, right? You can buy a server that has dual core, quad core, or we can add multiple servers. Then that combines quad core with series of 5 different servers. Each has a quad core processing capability. So you can kind of see where I'm going with it. The database will recognize or try to compile again, measurements, stats, right? Numbers, measures to determine what resource does it have and how does that factor into the equation of performing at the optimal level. Your processor speed, and then how much RAM, how much cache space I have to work with. So all of that plays into, again, optimization statistics. So important. Other more components, measurement tables, how many tables you have, how many rows of data in each tables, what are the, is it a long integer data type, or is it just a single value data type, one character, yeah, Y for yes, no, N for no, or you're talking about a blob. There's actually a database attribute data type known as the blob, which is, it can be a lot of characters. You can write a whole book into the one single cell. So the database need to compile those measurements to know, again, how much size am I dealing with? When you ask for table A is 100 row or 100 million rows of data that makes up 150 megabyte of zeros and ones. So when somebody writes a query against that table, the database needs to factor that in, as opposed to you're writing a query against a table that only has 1 kilobyte of data. Then it knows it can run that one very, very efficiently in the thousands of milliseconds, as opposed to some other giant tables that you're asking stuff from. So, and then whether or not the table has indexes, again, all of that are also data points that the engine had to optimizer has to take into consideration to find the optimal point. So in terms of looking at the query, the incoming queries that the database looked at in terms of trying to help optimize. So it's one thing to look at the hardware resources and use algorithm stats. It's one thing to look at your database construct of sizes, time of execution in conjunction with the hardware resources allocation. Now you also have to look at the incoming queries that's asking for it in the first place, how you can potentially optimize that SQL coming in conjunction to, again, to your data data context and then your hardware components. So there's three actually kind of component to query processing, analyzing it. In the database world, they look at parsing, execution, and fetching. So in a nutshell, we'll look at each one of them in a bit, but the database management system parses the SQL query and choose how to run them the most effectively, most efficiently. So literally, right, you look at the SQL and chooses the most efficient access or execution game plan of how you want to handle it. Keep in mind that when he says look at the query, a query can be as easy as select all from table A, or select all from table A where ID is 1. That's the simplest form of a SQL query. But obviously, as we know, the world of database and actual business is not that simple. So when you have a query that comes in, select something from something where you left join, and then what are you joining? You're left joining from this table, and then select from that table, and then when you select from that table, right join to another table. So when you have nested SQL statement, the database has to analyze all those statements, even though they are one giant one from a user perspective, but the database is able to analyze every single component to its simplest form to try to decipher what each of those nested statements is actually trying to do. And then when whichever table those nested statements are touching, it then uses those characteristics, statistical data, and an algorithm to determine how to deal with that. So parsing is an important aspect, the first at the forefront of it. Then you will execute the game plan that you came up with after the analysis and the execution plan. Then you will follow the plan and execute it, and then you will return the result, which is the fetching. All right, so let's look at how that works. So graphically, over kind of an overview of how this three works. So somebody is typing in the computer, and then a SQL is generated to be sent to the database. And then database go through parsing phase, right? The first leg of it is checking for the syntax. Did you have bad writing, right? Does the SQL statement actually is correct? Naming, access rights. Do you have the right to even ask for this based on the application of the user? And then you decompose and analyze all the components of your SQL statement and what you're touching. And then it will generate a plan, an access plan of how it plans to execute this. And then you will send the plan or store the plan in the cache for the database engine to then, all right, once I have a SQL access plan inside the cache, in the SQL cache, database will know I need to execute that plan. So then you go into the execution phase where you actually runs it. It does all the input and output operations. It adds the lock. Remember in chapter 10, the locks, two-phase locks, table lock, row lock. It does all of that stuff, and then it retrieves the data and then plays the data back into the cache memory, temporary memory. And this data that comes back is actually what the user were asking for. So that's where you retrieve that from the hard disk, right, from the drives. So once it execute, it pulls what it needs. It then put the results of what you asked for in the cache. And then finally, the fetching stage is literally saying, now that you have data in the cache, it's just gonna fetch those information and send those zeros and ones back to the user computer, where whatever the application the user was using would then format and present it to you in a way that you can easily understand what you're looking at. So that's pretty much in a nutshell the three stages. And then that's a graphical view. So in the parsing phase, here's a little bit more defined of what it does. So again, we talked about this, right? SQL is broken down to smaller pieces to look at every single element within your SQL, complex SQL, nested SQL, whatever. And then the query optimizer analyzes that to see what you're touching, the table size, and factor in all those characteristics. So the optimizer here is the process where it analyzes all your queries and finds the most effective way to produce that, that plan. So the optimizer process is the important part here in the parsing phase. And then once the optimizer does its job, the access plan is generated. So that's it. That's what the first phase is. So you can tell, right? The first phase is actually one of the most important one that gets everything kind of aligned and started. So if it's not optimized right at this layer of it, then you're gonna have inefficient execution because your access plan will be inefficient. Access plan, sample database access plan, IO, input output, right? So it does a table scan to generate stats. And then you look at the row ID, you look at your index. I think there's a slide I have to show you what how the index come into play. So when your SQL is trying to look for stuff, your SQL may be touching one table, or is asking for data that's going to be pulled together across 10 to 15 different tables, right? The complex SQL statement. Regardless of it, you're touching tables, and then each table has its own overhead. So that's what you're looking at. When the database is supposed to execute, you will try to analyze all of this part of it, and then you can see the impact, right? If you know the row ID, right, that's fast. It goes straight there. If you have index, then that's even faster. Then you have a quick lookup that will take you exactly where you need to go on which table, in which row, in which attribute. So if table that has index, it will perform much faster than any table that don't have index. So you can see there's a lot of dimensions of trying to optimize that you have to factor in. And that's what the optimizer or the database is gonna do. Let me see anything else I haven't covered here. So anyway, you can read through this. I think I hashed this out pretty much already. Let's get that. And then once you have the access plan, then the database is just gonna just gonna run it, right? Then it's gonna all the IOI input output operation indicating the access point are executed. So we talked about the locks, data retrieve, pull back, and we put in the cache and so on and so forth. So straightforward after the access plan is generated. And then you fetch the data that was placed in a temporary memory based on what the result sets were from your query. All right, so delay. Again, the infrastructure lecture I've gone through. Hardware is a major component to all of this. So hardware has limitations. They're one of the biggest component in performance and optimization. So back in the old days, right, if the computer is slow, the database is not giving me back the data as fast as I want it, well, guess what? Buy more hardware, right? Stack them up, make it more powerful, and they will run more. But that's at a cost. So as in today's world, the goal is not to build out massive, spend millions and millions building out infrastructure just because you want a faster response time by the database. That's why optimization by the database side of it, factor in the resource limitations of the hardware, becomes a little bit more advanced in terms of trying to use software to optimize as opposed to always just keep on buying raw power. So anyway, so that's kind of what this is talking about. Indexes. So this chapter talks through a lot of more mechanics of indexing, but I don't need you to go into that level of detail. What I need you to know is at least understand the whole concept of why indexing is useful, and then why is it really good to have that in terms of optimizing the database. So in a nutshell, right, if a table doesn't have an index done by the database, and again, as a database administrator, you can choose which table to create an index for, and then choose which table attribute you want to index. And the whole purpose of indexing a table is if your table is huge, it's large, it has a lot of data attributes, and then it has a lot of records, you will want to index that because you want to create a quick lookup table that allows, the optimizers, the parsing to understand, hey, if I'm analyzing this SQL that needs to be run, it's going to touch that table. And if that table has an index, I can run much faster because the index will tell me exactly where to go inside that massive table with massive volume of data. It will tell me where to go to pull exactly what I needed. Without the index, if there is no index, the database management system has to scan the full table to look at most of the element one at a time until it kind of knows where your stuff, what you want is at. And that takes a lot of resource, CPU power, and time to run through 500,000 or 500 million rows of record just to get a feel for where your SQL is asking and where is it gonna be at. So index allow you to remove a lot of inefficiencies that way. So I think I mentioned, right, it's like back in the days going to an old library. I think in my earlier chapters, I may reference this in the lecture. If you go into a library that has 1 million books, if you don't have a card catalog index, or if you don't have a computer that indexed where the books are at, for you to quickly pinpoint what you're looking for, author, title, or year of publish, or the publisher, right? So I only had to index 4 data points of a book. And then I put them in the card catalog where you can search out by either of the 4. I can tell you exactly which floor of the library, in which shelf, under which number you will actually find the book. So you can go from the card catalog index straight to where the book is. The alternative without index, without the card catalog, or whether or not it's, the 3x5 cards back in the old days, or you have a search, they put a computer for you to search and find your book. But what that computer is actually doing is just replicating what card catalog used to give us. It's an index of where every single book is at. So without index, whether or not it's a computer or a card catalog, the only option you have to find the book you want is start walking each shelf at each floor until you find what you want. So you can you see why indexing is such a efficiency component. It was optimizes the database is an important component to doing so. So this is kind of graphical example, right? You're indexing some information, some raw data. So when a database try to analyze where you need to go for your statement to find what you want, it actually look through this to find and then go straight there, as opposed to go down this one at a time until it finds what you want. So there's a graphical view of that. So indexing, just make sure you understand up to what I described from the book and everything that goes into the hash and whatnot. Just, you know, I don't need you to go down to this level. So I'm gonna skip all this. So choices, rule basis versus cost basis. So the database must kind of have to choose what index it uses and how to perform the operations. So when it does that, there's two choices. Rule-based, which is, you know, you said user presents set of rules to determine the best way to run this, to run your query, or it's cost-based, which then use again, algorithm-based stats about what you're accessing and what you're pulling back, what you're touching inside the database. And then it determines which is the best route. So one of the key thing is when it says cost between these two types, it's looking at how much resources that you need to consume. That's all. So the cost is not really dollar and cents per se. When you read through this chapter, just recognize, right? The cost is saying how much resources am I gonna tie it up to do in a one way versus the other. And then therefore I should optimize by choosing the lower cost way. But in terms of choices, it looks like, again, all the elements we discussed, the data point to analyze the statistics to then derive at this point of making a choice, which one is more cost effective in terms of the resource allocation or overhead to actually run what I need to run. All right. Skip this part. I don't need to go down to this. So yeah, just kind of understand the definition of this and the concept behind it, and everything else you can skip. So yep, let's skip this. All right, SQL performance tuning. Bottom line, I think up to this point you have written some SQL statement. You can kind of get a point. There's multiple ways to write SQLs to get to what you want. So a good SQL administrator, database administrator, can write very efficient SQL. They can know how to use complex joins to pinpoint exactly what they're looking for. Or a bad SQL writer will write series of SQL statement that will pull large amount of data back and put them into a temporary table, and then write another SQL to look through this temporary table to find what they want, that generates another temporary table, and then write another SQL to then look at the subsequent temporary table. And then so they do it the long, hard, expensive way of keep on pulling massive amount of data back, write another query to say, all right, now look through what I just pulled back and find what I want. And then I look through it, I find a grouping of what I want, and then I write another SQL. But every time you do it that way, you're creating large blocks of temporary data that's being fetched, which causes a lot of, you know, in and out, input and output, which consume a lot of hardware overhead. So there is definitely SQL performance tuning where you reanalyze how you have written your SQL. At the end, both way of writing can get you what you want, but one can be ran and executed based on the access plan and whatnot, maybe in 2 milliseconds. While the other series of SQL, once you finish running them, it took you 1.5 minutes to achieve what you want. So again, 3 milliseconds and 1.5 minutes, that's a lot of overhead consumed by a bad written SQL. So that's a very important aspect of what, as a user, as a programmer, we have control over how we actually contribute to the optimization of how the performance of your database operates. I'll give you an example. You know, we work on this property tax system with a vendor for a long time, many, many years. We have a software on our database that monitors the optimization efficiency of the queries that's written by the vendor. And literally, it's no joke. The example I just gave you, we have SQL queries talking to our database that took 3.5 minutes to get what it wants. And my own database guy look at and analyze, why does that SQL take so many minutes to run just to get back what it wants? Keep in mind, when a query took 3.5 minutes to run, that's because a user somewhere click on the button and say, all right, I need to do this. And once I click it, I can see the result. So the user clicked the button. So what happens between the user clicking the button and the SQL taking 3.5 minutes to run? Well, guess what? We call it the circle of death. Users are sitting there looking at a spinning circle for 3.5 minutes before the website, the web application, showed them the data that they were looking for. So they stare at that thing turning for 3.5 minutes before the page continued to show them what they just click and ask for. So then we analyze, right? Because immediately we get users complaining about the performance of the system, because nobody wants to do, every time they click on something, they're going to wait 1 minute to 3 minutes before you respond. Think about it. If you go to iLearn, whatever you do in iLearn, every time you click a button inside iLearn, you wait 3 minutes. That is not going to be pleasant. So my guys open up and look at the access plan, look at the SQL query, the parsing, and all that stuff. So they look at the actual statement and determine that it was such poorly written SQL statement that my database guy rewrote it. And then we tested what we rewrote, and we're able to get to down less than a minute, 1.5 seconds. That retrieved the same thing just by rewriting the SQL statement. So then we send that over to the vendor, and the vendor use, you know, our code to change out their code. So how you write SQL is very important in terms of performance as well. So there's tools for us to monitor and optimize even at the SQL level as we write them. So that's what SQL performance tuning means. We're tuning how we were written, how the SQL statements are written at the front side of it before we send it to the database. Index select, again, I'm more into the index part, so I don't need you to know this one either. We'll skip it. Conditional expression, I will skip this part as well, so you don't have to worry about this part. I'm gonna skip, this is part of that. So I think, well, step to formula query. So it's straightforward. You pinpoint what column and what are you asking for. Identify your source table, decides how to use join. Again, don't try to write select, nested select, a lot of where. Sometimes join will satisfy a lot of those complex wheres and whatnot conditions. And then, so it's just, again, think through a good practice of writing SQL, how you will think through what you're about to write. So that's what the steps are talking about. Again, some important, I think, important part here is the cache, right? The memory, the data cache, the SQL cache, the source cache. Those are all memory spaces allocated for database. And then the database use cache because cache is the fastest memory space that can allow us to move information or zeros and ones across the cache memory. So database is utilizing that a lot to function, to use its optimizer leverages that capability, that fast temporary memory space to handle its resource allocations and what it needs to do. So the data cache must be set large enough, for example, to permit many data requests and to be serviced from the cache as possible, because cache is the fastest place to service anything. So they want to maximize what they have. I would conceptually, I'll draw a comparison, right? A lot of you or us, when we buy computers, we look at how fast is the CPU, right? i7, i5. We look at the RAM size, 16 gigabyte, 8 gigabyte. And then we probably will understand enough now about, I want solid state drive, so we look at those three components. But one more component that a lot of people probably don't look at is actually the cache memory. So the cache memory sits between the RAM and the CPU. And it usually comes into 3 megabyte cache memory. That is actually, if you want the boost of your performance, I think in my infrastructure lecture, I talk about, look for SSD drives. It will give you a huger boost than the faster CPU in some occasions. But the larger cache actually gives you even a great boost as well. But a lot of people don't understand. They don't look at the cache. They look at 2 megabyte cache, or you're buying a 3 megabyte cache, or 6 megabyte cache. I don't know how far they go. That actually means a lot in your performance. So when database is saying those data cache, SQL cache, store cache, they're also talking about the cache memory that sits between the RAM and the CPU, and it's going to fully utilize that speed to store stuff that it needs to access in a fast pace and shift data between those cache memories. So from the performance standpoint of view, those in-memory such as cache and or RAM, in-memory databases eliminate the bottleneck that you would have tried to retrieve data from a mechanical hard drive, a permanent storage, right? Remember we talked about the permanent storage, the hard drive is the bottleneck because it has mechanical parts that is trying to read data physically and then send it back to your chip-based, bus-based memory spaces that doesn't have any mechanical parts. So they shuttle zeros and ones at speed of light. So again, two major components that you had to make sure you kind of walk away understanding the concepts behind them. Some other recap, I guess, some important notes, right? Input, output, accelerators, RAID. I think I talked about it in my infrastructure lecture. Redundant array, so literally series of drives, hard drives that can allow you to have certain level of redundancy or fault tolerance in case you lost zeros and ones in one of the hard drive. It needs to be recovered because you cannot just keep a single copy of your most important data. You want to have a way to have multiple copies and or the ability to recreate the original sequence of zeros and ones so that you can piece back together the original data or information. Disk contention is just multiple sources is try to command the disk to perform same thing, to perform things concurrently. So you have contention, right? People fighting over the sequencing or the control over it. So those are known as the contentions. So you kind of get the point. If you read through this, it's all just, again, some other important elements into performance tuning. Some of them we already covered kind of with examples in prior lectures. This is the rate table. So for those of you that do, so in my infrastructure lecture, I talked about the SAN, S-A-N, storage array, a network storage array. And then because you have so many drives, you want to make sure the data stored on the drives are actually replicated as a backup. So you don't lose or you ever have a chance or probability of losing data because there's only one copy somewhere. So you can use a software that will control your hard drive, and the software will allow you to choose what kind of RAID level you will like, because RAID is actually trying to help you to have redundancy. So if you choose RAID 0, that means the data blocks are spread over drives, known as stripe array, which I talked about in the infrastructure lecture. And then if you do RAID level 1, here's the definition of what the storage array will actually do if you chose to have RAID level 1 applied to all the drives. If you choose level 3, that's what it means. 1 plus 0, here's what it means. So the biggest one is definitely 1 plus 0, which give you full redundancy. Literally, you have everything duplicated in 2 complete 100% matching sets, which means it takes up twice as much of space every time you use 1 plus 0 level. So that's RAID. Now, one thing I will say, in the at home, so not only a SAN that I explained in the infrastructure lecture, you can buy a mini SAN at home, a home storage, a home SAN that has 2 drives, or that has 4 drives, or that has 8 drives or 6 drives. So for those of you that have a lot of data, and then you're concerned about losing them, or it's too much hassle for you to always manually copy to another hard drive every time you store something because you deal with a lot of data if you're a graphic designer, so on and so forth. So if you don't want the hassle of manually try to keep 2 separate drives and then manually backing them up each other, you can go buy a SAN for home that costs you, I think, $200, $300. You can have a dual bay SAN, and then you slot in two drives that's equivalent, 3 terabyte, 3 terabyte. And then that little device will allow you to configure the RAID. For example, I have one at home just because I have a lot of family pictures and videos. I have over 1.5 terabytes of data. So obviously those are the things I can never ever replace. So I bought a SAN for my home where as soon as I copy something onto that SAN, the little device itself has a RAID of 1 plus 0. It automatically replicates the data onto the second drive. So I have 2 slots, and then I monitor the 2 lights. If one of the light goes dark on me, I just need to pull it out and slot in another drive, and then it will replicate and it rebuilds the redundancy again. So it minimizes the chance of me having lose my only data. So this whole RAID and SAN concept is actually for your home as well. If you have important data that you wanted to keep and protect it, you can buy that device. So in the infrastructure lecture, I share with you what a big company would do, right? 100 terabyte. But at home, you can do a SAN for 2 bay, or you can buy 6 bay, however. So you can Google it, you can find out, and there's a lot of people selling that stuff. And then on top of that, by the way, let me just add to that. I'm so cautious with my data. So even though I have that at home, I have RAID 1 plus 0 from all my own personal files. I also ship that 1.6 terabyte up to the cloud storage. So I pay, I think, $6-7 a month to then constantly load everything inside my SAN drive. Every night it ships whatever's new up to the cloud, where I have another copy in somebody else's infrastructure. So I have literally double redundancy. So I will make sure I never lose those information or data. All right. So anyway, RAID levels, that's what it's all about. That's it. This is the last slide. All right. This is chapter 11. So the remaining 2 chapters, I think 13 and 14, we'll kind of look at, some of the business side of things. I think this pretty much wraps up the components of the database, all the technical stuff. And then the last 2 chapters, we'll start to look at what's in the horizon, as well as, how does this actually kind of present itself at the business level of it. So 2 more chapters, lecture coming. All right, thanks.